Hello and welcome to this video lesson. In this video lesson, we will be looking at an example which involves power and efficiency. The question starts off like this. We got Julian who gets on the physics truck and starts to drive uphill. The height of the hill is 800 meters and he travels 2 kilometers. His final speed at the top of the hill is 15 meters per second. The combined mass of Julian and the truck is 1,000 kilograms. If the efficiency of the engine is about 50% and he experiences an average frictional force of 120 newtons during the trip, determine the chemical energy required during this part of the trip and the power delivered by the engine. We're going to do this along with the efficiency as well. We're going to add that at the very end of the question. So if you want to take some time to look at the question, draw a system diagram, draw some force diagram, and if you want to draw the energy bar charts for it, you can, and after that we can kind of get started. You can try it out and check your answer at the end. Okay, let's draw out the situation so we get an idea about how to start this question. I'm going to try to draw a hill. And at some point here, we get the truck, which starts here. And let's say it ends somewhere here. It really doesn't matter where it ends. We know that the truck has traveled a distance of 2 kilometers as stated in the question. So that's about 2,000 meters. So I'm going to change everything into the fundamental units. And we know that the height that the car has traveled, so I'm drawing these approximately to the center of the masses, is 800 meters. We know that the initial velocity is equal to 0 because it starts at rest. And we know that its final velocity, v2, is equal to 15 meters per second. We know that the combined mass is is exactly 1,000 kilograms. And what else do we know? We know that the efficiency of the system, or the efficiency of the engine here, is actually 50%. Good, and I'm just going to check all the information, and I can see that this first number, the height, is given in 4 significant figures. This is given in 3, 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 so my lowest number of significant figures is 3. This one is also 4. So my final answer has to be given in 3 significant figure. This is great. I've already started. I have a system diagram, and I'm also going to draw the forces on my system. So I'm going to use orange here, and the forces acting while it is doing the trip. We know that we're assuming constant acceleration. There's going to be a force, and that's the applied force, is the force by the engine, and you can also call it the chemical force. You can call it other things. I'm going to call it engine force here. There's going to be a normal force acting normal to the surface, and there's going to be a gravitational force acting downwards, and probably slightly bigger. So I'm going to redraw this. I'm going to add a little bit to it because I know that this component of the force should be same as the Fn because the object isn't accelerating into the ground. And this is Fg, and the force going backwards is going to be the force of friction. And if you folks are in the IB curriculum, this is the reaction force, this is W. Looking at what type of forces are acting during the trip, so looking at the forces or work that's being done, work is always done by forces that are acting or components of forces that are acting in the same direction that the object is traveling. So in this case, we know we have a component of gravitational force that's acting on our object. We know that the engine force is acting in the same direction as the displacement, and force of friction is acting uh, exactly opposite to it. So we know those are, and there is the reaction force or the normal force acting, but it's 90 degrees to the direction of displacement, and therefore it doesn't do anything in terms of work. And based on our forces, we know that the gravitational force is a conservative force. We know that these two forces here are non-conservative forces, and they're external forces. The engine force is coming into our system, and that's allowing it to actually get for the car to gain gravitational and potential energy, and the force of friction is working against our system, so that's the energy that's coming out of our system, and that's a mix of thermal radiation and sound energy that's actually exiting our car, and it's actually lowering the amount of kinetic energy and the potential energy that our vehicle can get. So we're going to draw a diagram which will signify how the energies are for our car between stage 1 and stage 2. Okay, I'm going to start drawing this like this, and we're going to have the kinetic energy of the vehicle at stage 1. We're going to have gravitational at stage 1. There's going to be two external forces or non-conservative forces, so I'm going to draw two sections for those, and I'm going to call this one work done by the engine and this one work done by friction. And I'm going to add these plus this, and this is all going to equal to the kinetic energy at stage 2 and the gravitational energy at stage 2, or the gravitational potential energy. Okay, in terms of kinetic energy at stage 1, we know that velocity is 0, and therefore there's no energy, no kinetic energy at stage 1. We know that at stage 2, it's going to gain some speed. It's going to be at speed 15, and because of that, it's going to gain some kinetic energy. So I'm going to add that kinetic energy over here. And in terms of potential energy, at the beginning, it's going to be at a lower height. We're going to use this as a reference point. So this is kind of like the starting point. Let's say that's height 0. And because of that, it's going to have no gravitational energy at the beginning, but it will have some gravitational energy at the end. So I'm going to do 0 here, and we're going to have some gravitational energy at the end. And I'm going to highlight that using orange. Now, in terms of the energies, we can see that we get 0 kinetic energy, 0 gravitational energy, but we have some energy here, kinetic energy, and some gravitational energy, and these energies need to come from somewhere. In addition to these energies here, as the car is traveling upwards, it's going to lose some energy due to the frictional forces of the tire touching the surfaces, and that frictional forces is going to reduce the total energy from from stage 1. So we have to draw that as well. And we're going to draw that. I'm going to use red for this one. And that's going to be a small kinetic energy, which is being reduced due to friction of the car as it's traveling upwards. So now looking at the energy, we have 0 energy, we have 0 energy. Some energy is being reduced here due to the frictional forces as the car is traveling upwards, and we gain kinetic energy and we gain gravitational energy. So that energy needs to, all these energies need to come from somewhere. And obviously in this case, the energy is coming from the engine. So this bar needs to be the tallest. It needs to be the absolute value of this added to this plus this. So the bar is going to be higher than these two and a little bit, and adding this to it, I'm going to draw that with purple, and it's going to look something like this. So this is the energy coming from the engine. I'm also going to write the energy transformation for this. We're going to start with some chemical energy. That chemical energy is going to be transformed into the energy of the engine plus some waste. And that waste is going to be thermal. It's going to be sound. It's going to be radiation from the engine. So as the car is traveling upwards here, we can see that it's going to lose, the engine itself is going to have friction in it. So you're going to hear some sound coming out of it. You're going to hear, you're going to feel some heat coming out, and that heat is going to have thermal energy. It's going to have some radiation. And there's also other things as well that we can actually add here. There's going to be some energy in the electricity, providing the car with other forms of the radio and everything else. So this waste energy is going to include all that. And because of this waste, we're going to lose 50% of our energy. So only 50% of the chemical energy is going to be given out. And out of those 50 of them are going to go to waste, and that's this energy here. And 50% is going to go to the engine, and that energy is going to be our output energy that's going to help the car move forward. Now, from those energies there, we're going to have some efficiency here, and that engine, the energy from the engine, that 50% of the energy of the engine is going to be transformed into gravitational plus the kinetic energy of the car because it's gaining some speed, so that's the kinetic. It's gaining some height, that's the potential. And there's going to be some waste energy, and that waste energy is the frictional energy, and that's going to be contributed to thermal. It's going to be contributed to sound, and it's going to be contributed to radiation and other forms as well. So there will be other forms as well because friction always causes different waste energy. And because of this waste energy, we're also going to have some sort of efficiency here. We don't know exactly what that efficiency is at the moment. If the frictional forces are really, really high, this efficiency is going to reduce. It could be, if the frictional force is very small, you might have an efficiency of 95 to 100, or anywhere between 90 to 100. But if this frictional force is very, very large, the efficiency could drop to lower numbers like 70s or even less. And the useful work we're getting out of this is a combination of these two. So we got that chemical energy in the car or the fuel that's gonna be transformed 50% to useful energy that's going to move or propel the engine or propel the car forward. Some of it is going to go to waste and different forms. And from that energy here, we're going to have some gravitational potential. We're going to have some kinetic, and we're going to have some waste again. And this efficiency is going to be considering this waste, and this is going to be considering this waste. Now that we've looked at this question and analyzed what's kind of happening, now we have to start solving it. So the first thing we need to solve is to determine the chemical energy. Cross-referencing back to this, the chemical energy is going into energy to the engine, and that energy is going to the kinetic and gravitational plus the frictional losses there. So we need to figure out what this energy here is, which is the engine. And once we find this, we know that that's 50% of the energy, the chemical energy. So then we can find the chemical energy using an efficiency equation, and we know that the efficiency is 50%. So at the moment here, we know that this plus this plus this plus this is equal to these two energies here. And we know that the non-conservative energies or energies coming or external work that's done on the system is going to equal to the change in energy. We can see that by if we subtract EK1 from both sides, EK2 minus EK1 will give us the change in kinetic energy, and subtracting both sides by EG1 will give us the change in the gravitational potential. So let's write that as an equation. I'm going to move my screen up a little bit to here so that we can see things a little bit more clear. And I'm going to start writing my answer. I'll use purple. So the work done by the external forces or non-conservative forces is going to equal to change in energy. And again, we can see that up here. So my work by my external forces is the work done by the engine plus the work done by the frictional force, and that's going to equal to the change in kinetic energy plus the change in potential energy. On the left-hand side, work of the engine is kind of what I'm trying to find, and the work done by the frictional force is going to equal to the force of friction multiplied by its the absolute value of the displacement times the cosine of theta. And that's going to equal to EK2 minus EK1, which is the change in kinetic energy, plus EP2 minus EP1, which is the change in gravitational potential energy. And sometimes I'm interchanging P and G. In this case, the potential energy is coming from gravitational. So just to change that back, I'm going to change this to G, 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 and you know that that's the gravitational potential energy. Good. I can now cancel some stuff out. So I'm going to use orange. I know that EK1, looking at the diagram, was 0. I know that EG1 is also 0, so I can cross those out. It was going to make my job a little bit easier. So this is going to cancel out, and this is going to also cancel out. And now I can continue my equation. I know that work done by the engine is going to, I'll write these down, FF displacement. Now, for my angle, just looking at my force diagram back here, I can see that my frictional force is going in this direction, so that's down the hill, and my displacement is up the hill. So the angle between the two, if I were to draw these out, I'm going to draw them out here so we can see them. Force of friction is going in this direction, displacement is going in this direction, and the angle between them is 180 degrees. So I can put that in here. That's cosine of 180. That's a bracket. And that is going to equal to the kinetic energy at point 2. That's half mv2 squared plus the gravitational energy at point 2, which is mgh2. Good. And I'm trying to find WE, so I'm going to rearrange for it. And it's going to be 1/2 mv2 squared plus mgh2. And I'm going to subtract by force of friction, displacement, and cosine of 180. So I'm subtracting both sides by that work of friction. So this is going to equal to 1/2. I'm going to start plugging in my numbers. The mass is 1,000. Velocity 2 is 15 squared plus 1,000. My gravitational acceleration is approximately 9.8. My height is 800 meters. I have my force of friction. The average force of friction acting on it is 120. The displacement, the car is traveling a distance of 2,000 meters, and cosine of 180 is -1. Adding these all together is going to give me 8192500 joules, and that's the energy that is required by the engine to actually move the car that much. And we know that the efficiency is equal to 50% for the engine. And here, what we have calculated are these three, and these three are the work done by the engine. And we know that the engine is the engine is 50% efficient. So the efficiency is going to be 50%. That's going to equal to the work done by the engine divided by the total energy by the chemical, or WC, or you can think of this as the energy out or workout, and this is work in. And what we're trying to find is WC, so WC is going to equal to WE, which is the work by the engine divided by the efficiency. And we know that this is 8192500, and we know that the efficiency is 50%. So I can just put those into my equation, into my calculator, and I will end up getting 1638500 joules. And because I need my final answer in three significant figures, that's 16.4, megajoules. Mega for 10 to the 6. The next part of the question is asking what is the power delivered by the engine. So the power delivered by the engine is this power, which is the work done by the engine, which is this much. So we're going to use that at the moment, and I might add an extra question to this as well, just to get your understanding up a little bit. But for the first part, we know that power done by the engine is going to equal to the work done by the engine divided by the time it took for the engine to do its work. So we got to find that time, and basically based on our system diagram in the beginning of the question, we know that v1, velocity 1 is equal to 0. We know that velocity 2 is equal to 15 meters per second. And we know that the change in distance is equal to 2,000 meters. And let's just say that's in the forward direction. And velocity is also forward. And we want to figure out the change in time. From my kinematics equations, what I need is, I'm going to add these. The displacement is going to equal to the initial velocity plus the final velocity over the change, over 2 multiplied by the change in time. And if I rearrange for time, it's going to equal to 2 delta d over vi plus vf. And if I plug in my numbers, I get 2,000. I'm taking forward to be positive here, divided by vi, which is 0, plus vf, which is 15, and I will get 266.6 repeated, and that's going to be in units of seconds. And now that I have this, I'm going to enter the value of my engine, 182,500, divided by the time, which is 266.6 seconds, and I will end up getting 307 to 1.8-ish, which in 3 significant figures will be 30700 watts. And this is going to be my answer to the second question. And now I'm going to add the question slightly, and the wording of the question is actually very, very, very important. So I'm going to ask, determine the power delivered to the engine during this trip. And now I have to do a little bit of analysis of, like, just in terms of wording, looking at this, it's saying determine the power delivered to the engine. It's not saying delivered by the engine, it's saying delivered to the engine. So I'm going to go back and look at this diagram for a little bit. And I can see that the power of the engine is over here. I know that the power delivered to the engine is coming from the chemical energy, and to figure out the energy that has gone to the engine, I have to go back to the chemical energy and calculate that. So I'm going to go back and do that. I already have the time it takes calculated in the previous question, so, and that's the 266, so I'm going to leave that up there. And I know that the power is going to equal to power done by the chemical energy is going to equal to the work done by the chemical energy divided by the change in time. And I already have all the values. This work is 1638500. The change in time is 266.6 repeated. And by doing this, I will get 61443, which is approximately 61400 watts in 3 significant figures. And you could have done this in many other ways. You could have just multiplied it by 2 because you know the efficiency was 0.5, or you could have used other methods as well, but this is one of the methods to get there. I'm going to add one last part to this question, and that is to determine the total efficiency of the system. When we're asked this question, I'm actually going to scroll back a little bit and talk a little bit about our diagram here. And we can see that what was happening is we had the energy coming from the chemicals or the fuel that has gone to the energy of the engine, 50% of it, some of it has gone to waste, and that energy from the engine has then gone to the energy of gravitational potential, kinetic, and the energy that was wasted here. So that's the W is standing for waste. And there's an efficiency here, and there's an efficiency here. So there's 2 methods of solving this question. One of them is to find this efficiency value. This is efficiency 1, and this is efficiency 2. And if we multiply the 2, we should get the total efficiency of the system. To find this efficiency, we have to divide the total useful work, which was EG plus EK, at stage 2 because the change is because the EG1 and EK1 were both 0 in terms of values. So these two divided by the energy coming from the engine. And if we do that, we will find this efficiency, and then we can multiply it by 50%, and that will be the total efficiency of the system. The second method, which also works, is we know that our useful work at the end is these 2 energies, which is the gravitational gained and the kinetic gained. And our initial energy is EC. And since we have we can find this very easily, and we already have this. We can just simply divide this by this, and we should get the same answer. So we're going to try both methods and make sure that they work. I'm just going to write the equation again. EC is equal to E engine plus E waste, and this is going to be EG plus EK plus E waste at stage 2. This one, the second waste is mostly from the friction, and the first one is mostly from things that are happening in the engine. So we know that this is efficiency 1, which is 50%, and we know that this is efficiency 2, which we don't know the value to, so that's what we're going to calculate next. So efficiency 2, this is method 1. I'm going to write method 1 in blue. Is going to be EG plus EK divided by the total energy of the engine, which is EG plus EK plus E waste, which is the frictional in this case. So we know that EG is EG is mgh, that's height 2, plus EK, which is half mv2 squared, and EG is mgh2 plus half mv2 squared, plus the waste. The waste is the frictional one, which is the force of friction multiplied by its distance, multiplied by cosine of theta, which we don't have to include in this case because we're just adding all the positive values in this case. So putting all the values in, we will end up getting approximately, or I'll just write the value as exact as possible, 97.07% here. And the total efficiency total is going to equal to efficiency 1 times efficiency 2. And in this case, that's 50% multiplied by 97.07%. And that's going to equal to approximately, I'm just going to write it in 3 significant figures, 48.5%. That was one of the methods of solving this. The other method of solving this is dividing the total useful work, which is EG plus EK, and dividing that by EC, which is the chemical. And we have all those values, so we can go ahead and do this. So efficiency total, this is method 2, is going to equal to EG plus EK, and we're going to divide that by EC. So we know that EG is going to be calculated by mgh2 plus half mv2 squared. We're going to divide that by the chemical energy, which is 16,385,000. And if we plug everything in, we should get 48.5%. And sorry, this is efficiency total, not efficiency 2. And those are just 2 different methods of solving the same question. When you get a question like this, just look at what is the best way of solving it. In this particular case, it was a little bit, because the first part of the question had asked us to find the chemical energy, then it's the easier way to is just to add these two and divide it by EC. It just takes less line to finish. But if you weren't given that and you were given that this is 50% and you were given enough information to just do EG plus EK divided by the total energy of the engine, which is these 3, then you could have just found this and multiplied the 2 efficiencies to get at 48.5%. So again, it doesn't matter which method you use, you should get the exact same answer. Just choose the most efficient way of solving the problem. I hope this this question and answer helps you get a little bit better understanding of power and efficiency.